Starting now. So I want to do this video on eigenvalues and eigenvectors. I don't really know what to achieve with this. I sort of just want to do it for fun, sort of as like a record for myself of topics that I learned in my undergrad. I'm not too sure yet if I'm going to be doing, or if I'm interested in doing, maybe topics that I'm also learning currently. I'm not sure how comfortable I feel, but definitely things that I've learned in past courses that I've already taken. And I don't have a particular order. I don't want to do like a tutorial series, I don't think, like on linear algebra or calculus or something. I think I just want to pick topics from my computer science and math undergrad that I like and just talk about them, and then maybe give some easy examples and show how to solve some problems using them. And so I figured I'd start with eigenvalues and eigenvectors, which seems sort of like a out of the blue topic, but I have a very long personal relationship with them because I learned them first when I took ordinary differential equations, and I had really no idea what they were. I didn't understand why, when we solve a system of linear differential equations, we use eigenvalues and eigenvectors. But then I took linear algebra after that, and everything became clear as to what they are. And so I figured I'd empathize with those who don't understand them as well and try to explain them in a more intuitive sense, as well as a rigorous sense, what they are, and then go through two basic examples of how to find eigenvalues and eigenvectors. And then I also thought I'd list why they might be considered important in computational fields. So what is an eigenvector? Or an eigenvalue? So when we describe a system of linear equations, we generally put it in this form, ax equals b. And there are many ways to solve this. There are many different methods using just Gaussian elimination, different matrix factorizations, such as singular value decomposition, or QR, or LU, or Cholesky. It's a pretty big field in computational mathematics, trying to develop algorithms to better and better solve these. But when we're concerned with eigenvalues, we want to take this idea and find a system such that AV equals lambda V. So we want to solve a system in terms of AV equals lambda V, where lambda is our eigenvalue, and then V is an eigenvector corresponding to lambda. And so what does that really mean? Well, in a technical sense, an eigenvector of just some square matrix is just a vector that in itself yields a scalar multiple of the original vector that you get when multiplied by the matrix. So if you say that A is a matrix and V is an eigenvector of that matrix A, then we come to AV equals lambda V. Again, where lambda is the eigenvalue corresponding to V. But in an intuitive sense, they really represent a scaling factor. So it all has to do with linear transformations and matrix transformations, which are very important topics in linear algebra, especially for computational things that I'll mention in the why are they important section. But you can think of it in a way that these eigenvalues lambda are scalars. So these are scalars. So lambda is just an element of the reals, and V is an element of Rn, so the vector space. So you can think of these eigenvalues as scaling factors by which the actual eigenvectors are like stretched or compressed or transformed by some matrix. And so conversely, I guess you could say eigenvectors represent the direction for which this transformation, this compression or stretching takes place, and what its simple scaling effect is. And so knowing that, the things that they're important in are things like, they show up in physics a lot, primarily differential equations, because we want to know how a system of differential equations will act over time. So we get solutions to differential equations that might look like this. Say this is a system of two equations. And you don't need to know where I got this necessarily, but this is generally a general form of a general solution to a differential equation. And for a system of linear differential equations, you might see this to where this solution has our eigenvector v and our eigenvalue lambda. And so if we're like doing some phase plane analysis and we're looking at what a differential equation might do over time, it could have some form like this, and you might be interested in how much, I don't know what it's doing there, how much this eigenvector scales over time in relation to the differential equation. And that's when I first saw them. I first saw these in differential equations doing this. So finding different phase plane graphs and general solutions to differential equations. And depending on what kind of eigenvalues you have, you'd have different phase planes. Basically, you had like real eigenvalues, repeated eigenvalues, or complex eigenvalues. And so they take place in things like image processing. They show up when using singular value decomposition in image processing to like decompose an image into, I guess, different constituent parts. So researchers maybe focus on efficient storage and like transmission of these images, and eigenvectors would show up in that. And then also, for someone who's interested in computer science, it's a very large part of Google's famous algorithm, what's called the PageRank algorithm, which is the algorithm that Google developed and uses to rank web pages and search results. And so that algorithm actually relies on eigenvalues and eigenvectors. I think it might be a little above my head, but I do know that it uses graph theory and eigenvectors, treating nodes in a graph. And it has something to do with calculating the importance of each node or page based on their eigenvector corresponding to something. But so I sort of just wanted to give this infomatic on, what are they, and, why they might be important and where they might show up for you in undergrad. You might either take linear algebra first or differential equations first, but they will definitely show up in either of those courses. I don't see a reality where you don't learn about eigenvectors in those courses. Or maybe you see them in physics first. I wouldn't be too sure. I only took mechanics and E&M. But now I wanted to go over just an example of how to find them. And so the general algorithm in like an intro linear algebra course that you might use to find them. I'm not going to be proving any of these derivations or these formulas used for these derivations, but you'll learn how to prove them when you actually take a linear algebra course. But for now, we don't need to be too concerned about that. But so for the sake of example, I'm just going to do a 2x2 matrix. So we're only concerned with square matrices. And I'm going to call this matrix A. And so let's remember our general form that we're going to eventually get to. So before we can find the eigenvector, we need to find the eigenvalues, lambda. So to do that, there is a very nice formula that involves a determinant. So we're interested in the determinant of our matrix A minus lambda, which is going to be our eigenvalues, times I, where I in this case is just the identity matrix. And we want that set equal to 0. Not the 0 vector, just the number 0, because this determinant is going to convert our matrix into a polynomial of some kind, either first degree, second degree, third degree. So the reason I chose 2 by 2 is because, for the sake of computation, this determinant will be very, very simple. We won't have to worry about cofactor expansion or anything like that. So we want to take our original matrix A, which is 3, -1, 1, 1. Then I'm going to use this bar notation for the determinant now, just so I don't have to write det. And then we're going to subtract lambda times I. So when we multiply lambda times I, we're just going to get a matrix that's 2 by 2, that's lambda 0, 0 lambda. And all we're doing there is we're taking the identity matrix, which in this case is 1, 0, 0, 1, and multiplying by the scalar lambda, which will just only put lambda in the entries that are non-zero. So again, this is equal to 0. And so now we can subtract this, which is very simple. We'll just go by component. So we have 3 minus lambda, -1 minus 0, 1 minus 0, and then 1 minus lambda. And so now we're interested in taking the determinant of this. So this is 2 by 2, so all we have to do is cross multiply these entries, which comes out to 3 minus lambda times 1 minus lambda, and then we subtract -1 times 1, so negative or minus 1 is just +1. It's equal to 0. So now let's expand this. 3 minus 3 lambda minus lambda plus lambda squared plus 1 equals 0. Lambda squared, -4 lambda, and then plus 4 equals 0. And so we could just factor this out. I'm just going to use... So the important thing to note here is that when you get to this point, we've now taken our matrix, as I mentioned, and converted it into a polynomial. In this case, we have a nice quadratic. And so just like you would in high school algebra, we're going to find the roots of this using either basic factoring techniques, completing the square, or in this case, I'm going to show you you can just also use the quadratic formula, which might be overkill in this case, but I'm going to do it anyway. And we're solving for lambda instead of something like x or y. So let's find the roots of this quadratic. So 4 plus or minus 16 minus 4 times 4 square root all over 2. And we see that we have a really nice solution here, because this is just going to come out to be 16 minus 16, which is 0. So we have the square root of 0, which just goes to 0. So now we have lambda equals plus or minus 2, 4 divided by 2 in this case. So we've found our eigenvalues. So we have an eigenvalue of 2 and an eigenvalue of -2. So these are our eigenvalues. So now we can use these eigenvalues to actually find our eigenvectors. So I like to list which one I'm working with, so I'm going to go for lambda equals to +2 first. And we want to recall AV equals lambda V. And there's a very nice derivation that involves the identity matrix to show this, but I'm going to guess that you're going to have the same situation I had when I first saw this and just be given the formula But basically, you can do some algebraic manipulation to convert this AV equals lambda V into the formula A minus lambda I times V equals to the 0 vector. And in this case, we know what lambda is now, so we'll fill that in. So we're working with lambda equals 2, so this gives us A minus 2I times V, where V is going to be our eigenvector, is equal to 0. Now note that 0 is now the 0 vector, because instead of just solving a regular equation, we're actually solving a system of equations. So to do that, let's just go through and fill out this formula. So A is still our original matrix. So 3, -1, 1, 1. And we're not interested in the determinant this time. So 2 times the identity matrix is just going to give us 2, 0, 0, 2. And then I'm just going to put brackets here, and our vector V, and the 0 vector. So let's subtract this. So we get 3 minus 2 is 1, -1 minus 0 is -1, 1 minus 0, -1. And I'm going to expand this vector just into a more clear notation. So I'm going to write it in its column form. So it's going to have components of V1 and V2. And then our 0 vector, I'll also just do that. It's just going to be a vector whose components are all 0. So now that we've gotten to this point, we can use any method as far as reducing matrices go. Or you could just go straight into back substitution. I'll just go through some matrix operations just to make it clear, because when you get larger systems, you might have far uglier matrices than this. But this is, we're pretty lucky here. This is a very simple problem. So 1, -1, 1, -1. But I see some very apparent cancellations that will just make our solution look a lot nicer. So I can flip the signs of these. So 1, -1, -1, 1. And then this, our augment is still 0. And from here I can add row 2 to row 1, and that'll give us 1, -1, and then zeros here. And so with this row of zeros, we've reduced it to echelon form. And so our back substitution is going to look a lot nicer now. We're just going to have V1 minus V2 equals 0. So in this case, 1 is what would be called our leading 1, if you will. And then this -1 is a free variable. So this tells us that we're not going to have a perfectly closed solution, but rather many solutions depending on certain scalar values. But this is very easy to approach, especially in this instance. So if we were to say, like, just focus on V1, if we were to solve for V1, we'd get V1 equals V2. So when we're finding our eigenvector now, it's going to be a vector V. We know it's going to have at most 2 components, as we're dealing with a 2x2 system. So 2 variables at most. So we don't know the values exactly for V1 and V2. We know that V1 can equal V2 and that V2 can equal V1, conversely. So to address this, all we need to do is isolate which one we want to focus on. So I'm going to focus on V2. So I'm going to rewrite this as V2 and V2. And the way you get there is just by, well, we know that V1 equals V2, and then V2 is still V2. So now to actually get numbers for a vector, we can factor out our component V2, And then that just leaves us with 1 and 1. So now we have an eigenvector v in terms of our component v2, and then the entry is 1, 1. So to be very specific, we'd say that this spans the set of the vector 1, 1. And this is what's referred to as our eigenspace. And so this would be an acceptable solution for your first eigenvector. So we've now found an eigenvector v corresponding to the eigenvalue lambda. And so that was just for lambda equals 2. So let's just quickly cover for lambda equals -2, which is just going to be the exact same thing, but with -2. So I'll do that very quickly. So lambda equals -2. So we have AV equals -2. So we have A plus 2I equals 0. So we have our original matrix 3, -1, 1, 1. Plus 2, 0, 0, 2 times v equal to the 0 vector. So 3 plus 2 is 5, -1, 1, and 3. So let's just go straight into solving this. I'm just going to go straight to back substitution. So I think I'm just going to go 5 v1 minus v2 equals 0. v1 plus 3v2 equals 0. And so we'll just solve this algebraically. So I think I'm going to just solve for v1 down here and plug that in. It's -15 v2. So that'll give us -16 v2 equals 0. And so we could just quickly see that v2 equals 0. So then v1 plus 3 times 0 equals 0. So v1 is also just 0. So this gives us a very simple solution for our eigenvectors. So we have v1 and v2. So our eigenvector v, v1, v2. And we have a closed solution, so we could just say that this eigenvector is 0, 0. And so you could specify it spans the set of the vector 0, 0 as our eigenspace. So for -2, it's quite boring. We just end up with a vector of 0, it looks like. I think my arithmetic is correct. It looks like it. And we found then that our eigenvector for this is 1, 1. So it spans the set of the vector 1, 1. So I'm not sure how helpful this might have been, but I thought it would be interesting to sort of just go over the basic idea of eigenvectors and eigenvalues. Now, one thing to note is that this is a very basic example. It's a 2 by 2 matrix, which is as simple as it gets for eigenvectors. And we have real roots, real distinct roots to be specific. And the larger your matrices get, as long as they're square, you can still do it, but your determinant is going to yield a much nastier polynomial. So rather than dealing with this nice quadratic to where you could just use the quadratic formula or something, or complete the square, just factor it, you might end up with like a fourth degree polynomial, or like even higher, or just a third degree polynomial. And so you'll have more eigenvalues. And really the most difficult part, I think, is probably finding the eigenvalues. I would say after that, the finding the eigenvector is pretty much just as simple as doing row operations or just straight to back substitution, and then understanding the idea of free variables so that you could formulate your eigenvector as something like this. But just make sure that in the computations you don't get caught up on this step with the determinant, because obviously if you have the wrong eigenvalues, then you're going to have the wrong eigenvectors. But I mainly did this just for myself because I thought it'd be fun, something I could look back on. But if this does help somebody, then that's definitely a plus. So I guess I hope you learned something new, or maybe you wanted to freshen up on some basic linear algebra. So yeah, thank you. I guess that's all I have.